All right, so we're back. This is day 2 of section 5.5. Get out of here. Don't spray my board. You're going to break it again.
Again. Look at that. I'm just trying to help you out. You see that? You're welcome.
Wait.
You're welcome for picking your boogers and putting them up there and me cleaning them off for you.
How you doing today, Mr. Paula?
I'm great. How are you?
Excellent. Did you need anything or just come to the house?
No, I saw that the other day when I was in shoe, so I thought I'd come back and
No,
do
you did not. No, you did not.
it. Why would I not do that for you?
Hey, how about those last 2 days?
Yes. Kind of coincidental.
No coincidence, those 2 emails got
Right
sent.
after the other one was sent out.
I know, right?
Interesting.
The teachers do not have to come in on the 2 days after the students get let out. Usually we might have to, depending on it's at the discretion of the superintendent. So like we are off on that Wednesday, and then like the teachers have to come back on the Thursday, Friday, but we don't have to this year.
Sorry, I'm here now. So.
What are you gonna do? You gonna put your height on there?
I am.
Just like a, careful now.
He didn't even.
You can't, you stood on that thing. You got some extra height there.
That's okay, he put it below.
Yeah.
So it's
Have you ever seen the height chart in my room?
I have, I'm on there.
Are you?
Yeah.
You're below me?
No, yeah, whatever.
Yeah.
All right. So section 5.5, the substitution rule. Remember, this is that U substitution, right? That's another name for this, the U substitution. What we're looking at here is figuring out something you could replace part of the integral with so that you can condense things or make things a little bit simpler so that we can find the integral and then reintroduce the variable at the end. That's really what we're looking to do, okay? And honestly, we just got to keep playing around with it, keep seeing the difficult stuff about it. Does the substitution rule work every single time? No. This is just very unique cases where it will work. So we left off here. All right. This is the integral of tangent of x dx. Now, what is tangent? Tangent is equivalent to what? 9 over cosine. Right? If you take my marker, is that what you came in here for? Tangent is sine over cosine, right? So this is really equivalent to sine x over cosine x dx. Now, there's really 2 different routes to take. We could either choose my u to be sine or my u to be cosine. It really doesn't matter what you choose. I'm going to, because it's just more difficulty one way or the other. So I'm going to choose the less difficult path. I'm going to say cosine x. I'm going to say u is cosine x, yes.
Is there not just a basic antiderivative for tangent?
Let's take a look. Let's go look at back at our, I was wondering that. Let's go back at the Net Change Theorem 1, and let's see if there's just a rule to follow. I doubt it because I know what the final answer is. Is there just a tangent x? No. So there's got to be some other weird, tricky thing that we've got to do with this. That's why there's a secant x tangent x, but there's no just tangent x. That's the answer, right? Yeah, that's here. So let's take a look here. So let's say u is cosine x. So what is du? What is du then? Just, yeah, it's negative sine x, right? Negative sine x dx. Do we see sine within our original? We do. Is it negative? No. So, negative du is sine x dx. And we do see a sine x dx, right? Okay, so I know that I can turn this into the integral of, I guess I could rewrite this to make it a little simpler as the integral of 1 over cosine x times sine x dx, just so we can truly see, oops, grab my x, sine x dx, just so we can truly see what we're substituting in. I didn't need to do that step, but this is really just 1 over u times what? Negative du. Right? And now we can actually do that, right? This is really just equivalent to negative 1 over u du. Right? And what is the antiderivative of 1 over u? Or u to the negative 1? What is that? ln. It's ln. Right? So this is equivalent to negative ln of u, absolute value of u, right? Definite integrals, we didn't have to worry about it as much because it was usually not taking into account negatives. But it's the absolute value, ln of the absolute value of u. Because again, why is it the absolute value? Because we can't plug in negatives into ln. We can't take a log of a negative number, so we got to take the absolute value of it. Plus c. And now we reintroduce our cosine x. Negative ln absolute value cosine x plus c. And again, the end result should always be a function, especially if it's an indefinite integral. We'll talk about definites in a second with this substitution rule. But if it's an indefinite integral, you should see a function, in the end, a function that does not contain u. I know I've not taught this before, but I'm guessing one of the main mistakes I'm going to see people do is try to leave u in your final answer. Can u be in your final answer? No, it should not be in your final answer. Why? Because we introduced that variable. We made that up. We have to take that back out in the end. So my final answer is negative ln of cosine of x, absolute value cosine of x plus c. The book does introduce this formula. I'm not sure if you need this in your homework or not, but it might be another good one to write down. Since negative ln of cosine of x is equal to ln of cosine of x to the negative 1, ln of 1 over the absolute value of cosine x is equal to ln of secant x. So those two things are actually equivalent as well. That's just another another definition that you need to know. I'm not sure if that comes up in the homework. I'm not actually done with making the key yet. So if you do run into that, you could make it equal to ln of secant of x plus c as well. So it's equivalent to two things. What we found before, the negative ln of cosine, absolute value of cosine x plus c, or positive ln secant x plus c. All right, now we're going to take a look at definite integrals. Now, how does this work with definite integrals? Well, because we're substituting something in as a new function, we can take a new function and make it our u value, right? Sometimes we could call it a g of x, right? That's what we do here for our substitution rule for definite integrals. We're creating a u value, a u expression, that's also another function, right? Because it's got that chain rule type thing going on with it. When evaluating a definite integral by substitution, two methods are possible. One method is to evaluate the indefinite integral first and then use the fundamental theorem. For instance, using the result from example 2, we know that this is the end result when we find the antiderivative. And then we just do top minus bottom, right? That's just standard, standard issue, right? Well, that's something that we probably don't need to learn. Because what did we do? Well, we did our antiderivative, we got done, and in the end we just did top minus bottom, plug in top, plug in bottom. But there is another way around it, and you guys might find that this is a little bit simpler. Because we reintroduce u, because we reintroduce a g of x, what you can do is apply the substitution rule so that you end up getting an, again, forgive me for the notation, an FU du, right? Within your integral. At that point, if it was an indefinite, we'd have to take u out and plug x back in, right? But what if we don't plug x back in? What if we leave it as a u? The only thing that it would need to change is our endpoints of our definite integral. So how do I change that? Well, what I do is I take those endpoints and I run them through my u. I run them through my expression that I substituted in. Okay? That's why you see the notation change from just two numbers here to the outputs of my function that I used for u. So above where I had my 2x plus 1, right? That was my u value that I used. That's my new function that I substituted in and out. What I could do is just substitute in my u, and then instead of plugging x back in the end, just change my endpoints to the things that would be, to the endpoints where if I plugged in those numbers, a and b, into that 2x plus 1, what the outputs would be, which is usually a pretty easy calculation. Let me show you what I mean here. Okay. We're going to do this using that 0 and 4. We're going to use this 2x plus 1 using that 0 and 4. So again, my u is 2x plus 1. You might call that your g of x. Here. Now, when I go to use my substitution rule, again, we'll go through this process again. Let me get this out of here. Right, this is something that we did the other day, so it's good to go over it again. It did yesterday. That's 2x plus 1. So du is 2 dx, right? So 1/2 du is dx. So that means that this can change into, I'm gonna leave it as an indefinite for right now. 1/2 square root of u du, right? When I change that into 1/2 square root of u du, I also have to change my endpoints. If I plug in 0 into this equation, what do I get? So that becomes my new lower boundary. If I plug in 4 into 2x plus 1, what do I get? 9. That becomes my new upper boundary. And now there's no need to plug in, to take out u and plug back in x. I can actually evaluate this, right? I can actually say, okay, well, this is going to be the integral of 1/2 u to the 1/2 power, right, du, from 1 to 9. And then say, okay, I've got 1/2 u to the 3/2 over 3/2 from 1 to 9, and now we can change it into that notation. Manipulate it a little bit. Keep change flip, right? That's 1 over 3, 1/3 u to the 3/2 power from 1 to 9. And at that point, I would have to take out u and plug back into x plus 1. But since I've changed my endpoints, I can now plug in 1 and 9 instead of having to go back in and plug in x. Okay? I can say 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. Okay? And I have 1/3 times 9 to the 3/2, 1.5. That gives me 9. Minus 1/3, right? Because 1 to the 3/2 power is 1. So 9 minus 1/3, the book gives me 26/3, but that's just 8 and 2/3, so 8.63. So how does this change things for definite integrals? Well, all we need to do is when we do the substitution rule, we can change the endpoints of the definite integral. And then end up just plugging that in as my two endpoints for when I evaluate using the fundamental theorem. Okay. Let's try another one. Let's evaluate this from 1 to 2. From 1 to 2. Okay, my u is 3 minus 5x. Right, 3 minus 5x. I can rewrite this a little bit if I'd like to just kind of clean it up. Because this is 1 to 2 of 1 over. And actually, I don't even need to write the 1 over. I can change that power to 3 minus 5x to the negative 2 power, and then times dx, right? That's going to help us a little bit later. So if my u is 3 minus 5x, what's du? Negative 5 dx. Be careful there. I know it looks like I almost see a negative 5, but I have already replaced 3 minus 5x with a u. So do I see a negative 5? I do not. So I'm going to divide it over to the other side. So negative 1/5 du is equal to dx. And now I can substitute that in. Now when I do so, I'm going to leave the endpoints off for a second. When I do so, I'm going to get u to the negative second power times negative 1/5 du. And now I can, well, I'll put the negative 1/5 in front. Oh, I'm sorry, I haven't done my endpoints yet. If I plug in 1 into u, what do I get? Negative 2. So that becomes my new lower boundary. If I plug in 2, what do I get? Yeah, 3 minus 10, negative 7. It doesn't matter that I've got numbers that are not in order from small to big. That's okay. Okay, so now I actually can take this negative 2 to negative 7, negative 1/5 u to the negative 2 du. And now we evaluate the antiderivative. So it's negative 1/5 u to the negative 1 over negative 1 from negative 2 to negative 7. Just make sure you keep it in order. Top goes on top, bottom goes on bottom, and now we do top minus bottom. Right, so those negatives will cancel out. This is really just 1/5 u to the negative 1 from negative 2 to negative 7. Again, I'm leaving off my plus c's now because we're doing definite intervals. Didn't say that, but we all know that. So this is 1/5 negative 7 to the negative first power minus 1/5 negative 2 to the negative first power. Let's see what we get. I get 1/5 times negative 7 to the negative 1. And I'm going to do that minus 1/5 times negative 2 to the negative 1. And I believe as a fraction, the book gave me 1/14. Yeah. So as a decimal, 0.71, or 0.071, excuse me, 0.071. 0.071. And that is 1/14. That's what the book is. Questions about that? Good there. Let's do one more of these. Okay, we're going to calculate from 1 to e ln x over x dx. What do you think my u is going to be? What do you think it's going to be? Let's try ln of x. Why not? That looks like the complicated piece of this. And if I was removing the complex pieces, let's how to remove ln of x. Okay, well, what is du then? What's the derivative of ln of x? Oh, look at that. 1 over x dx. And now do you see it? Can't this be rewritten as 1 to e of 1 over x ln x dx? And I could just reorder that to say 1 over x dx times ln of x. So this is really, I'm going to leave off my endpoints for right now, u du, right? Now, what are my endpoints now? Well, if I plug in ln of 1, what does that get me? Log base any number of 1. 0. And if I say ln of e, what's that give me? 1. Any log base of the same number, remember ln is log base e, so it's like log base e of e. Those cancel out, it's just 1. We could have plugged that in our calculator too, you know. ln of 1, ln of e. All right, now let's evaluate. Okay, we got u squared over 2 from 0 to 1. So top minus bottom, 1/2. Pretty simple, right? That was a pretty simple example.
We consider the when it's u, we consider that if it was just like x.
Yeah. Yep. We introduce that variable and treat it like that way. We're integrating that, like trying to integral with that.
That's the power of 1.
Right. U to the first power. So take it up 1 u squared. Okay. Now my last two examples, have to do with even and odd functions. Now this is again a very unique case. We've done the majority of the bulk of the work for this section already. This is just very, very unique cases when you have integrals of symmetric functions, integrals of odd or even functions, even symmetry or odd symmetry. Are y'all done? Glad you turned it in because I was just going to reference something that was on the test. Think back to the question on the test in the past quiz that was the parabola. Remember the parabola question? What ended up happening on either side? It was always what? It was always equal, right? The area on the left side was equal to the area on the right side. So it always ended up being, every time we did one of those problems, no matter how I changed the vertices, the zeros of the function, whether it was -6 to +6, or -5 to +5, or -7 to +7, every time we did that function, we ended up getting the same number minus a negative same number. And it ended up being double of that number, right? The reason that was happening is because that was an even function. I kept giving you an even function, one that was symmetrical about the y-axis. I didn't shift it away, I didn't take the axis symmetry away off the y-axis. I made it stay on the y-axis so that I had symmetry. So what we can really do is take that example and turn it into this rule here. If f is even, if you have an even function, that would mean that if you have the endpoints of the same value, a definite integral of the endpoints of the same value on either side, right and left, like we had that parabola -6 to +6, a parabola -5 to +5. If you've got an even function and you're trying to integrate it over the domain of the negative number to the positive number, where those values are the same on the left and the right side of the axis, then all you really need to do is take 2 of the integral from 0 to the positive of that function. Okay, that's equivalent. If it's odd, meaning if you take f of -x and -f of x, then going from negative a to positive a. If it's odd, it's going to end up being 0. Why is that the case? Well, because take a look at an example like this. If it's symmetrical like this, and it kept going, whatever. And it kept going here, whatever. And it's symmetrical. Isn't this area the opposite of that area? And they will always cancel out. And if it's not the same, then it's not odd, right? If it's not the same, then it's not odd. So if this is odd, those two areas are always going to be inverses of one another. They will always cancel out with each other. It will always end up being 0. So let me show you 2 examples of this. Let's take a look at an even function. Take x to the 6th plus 1. X to the 6th plus 1. Isn't that even? If I take negative x and I plug it in, doesn't that give me the original function back out again? Yeah, because it's an even power, right? I've only got even powers, and it's going to remove negatives, and it's always going to get us back to f of x. So since it's even, if I tried to take the integral from -2 to +2, that's like saying the same thing as 2 times the integral from 0 to 2, from the axis to 2. Now, does that help us any? Yeah, because isn't it really always easier to take the integral when the bottom is 0? Yeah, because you're going to end up giving it, especially when it's a polynomial like this, you're going to end up getting -0 in the end. So it's an easier calculation, right? Is it saving you a ton of time? No, not really. But it's just a nice trick you can use, right? So we do the same process. We find the integral, we raise it, divide it by the 7, take this as an x. What we can do is multiply by 2, going from 0 to 2. Plug in the 2, don't worry about the 0, and just multiply it by 2. Right. Let me show you an example of an odd function. Since tangent of x over 1 plus x squared plus x to the 4th is odd, like you all know that it's odd. Right? So, like, oh yeah, that one. That's odd. Since it's odd, going from -1 to +1 is always going to end up being 0, right? If it's an odd function, like this one here, tangent of x over 1 plus x squared plus x to the 4th dx, going from -1 to +1, going from -2 to +2, going from -3 to +3, going from -4 to +4. As long as you have endpoints that are the same value, just one negative, one positive, it's always going to end up being 0. I wonder what this looks like when we graph it. Let me just try to do this real quick. I didn't do this beforehand, so this might not look all that interesting, but why not? We got some time. Plus, oops, that's a minus sign instead of a plus. X to the 4th. Let's see what happens here. Might be setting myself up for nothing, but we'll see. Wow, that's a great looking graph right there. Let's see what the window looks like if I just go from like maybe just -2 to 2. Let's make our window a little bit smaller in the y values. Let's make our y minimum go to like -5 to +5. Reduce it down a little bit. Yeah, I mean, just that little thin strip in here, here is -1, here's +1. This is saying that because this is odd, that area is always going to be the same as that area, right? Just one's below the x-axis and one's above the x-axis, so it's always going to turn out to be 0.
Is that full function odd or just in those?
It looks odd. It looks odd all over the place. Zoom 6. Let's go back. I mean, there's obviously places where it's undefined, but yeah. Any questions about that stuff? We're good there? Because that's the last slide. Second to last section done.